Hi, and welcome to the first session here of our lecture on Introduction to Machine Learning. So here we'll just talk a little bit about basic terminology. So we'll talk about what actually is machine learning, what is AI, what is deep learning, how does that connect to statistics, and we'll discuss a little bit of what these major areas of machine learning are. So what is supervised machine learning, what is unsupervised machine learning, what is reinforcement learning. But after this very brief introduction, I'll pretty much simply focus on supervised machine learning for the remainder of the material, and we won't really cover these other areas here in this lecture. Okay, let's dive right into this. So I guess every one of you has already heard that machine learning is having a very, very strong and severe impact on on many aspects of our world. Also on many different scientific areas, many job areas. So I guess you already know that search engines are very often adapted and trained to output results by machine learning to reflect your search preferences. There are recommender systems on things like Amazon and so on that learn your taste in books, music or movies. There are algorithms to do automatic stock trading. This might also be an area where we don't necessarily always like all of these applications, and there are also certain risks associated with these things. We have really nice tools that can currently already very accurately translate between different languages. Most of you have heard of things like Deep Blue and Mind, so Deep Blue for chess and DeepMind, which now can beat humans at Go. I have played Go for some periods in my life, not super strongly. I can still remember years where the best computer program was not able to beat me, and now this has super drastically changed. Physicians are supported by personalized medicine, so we're using machine learning there to improve diagnosis, to maybe give some recommendations for certain treatments. And I guess everyone has heard of the current LLM revolution, so large language models, ChatGPT, and so on. And this has also very, very severe impacts on how people currently treat things like software engineering and coding. So certain parts of coding might be, semi-automized by these things. We might not completely agree with that being a perfect idea. I guess we still have to figure out how well this works. And there are also lots of data-driven discoveries already being made in physics, in biology, genetics, astronomy, chemistry, and so on. So many scientific fields are becoming, maybe not completely, but to a large degree, data-driven. So what does this have to do with, or how do things like artificial intelligence, machine learning, and deep learning now relate to each other? So many of us are not very, I would say, clean in terms of using these words. They are somewhat, the definitions are not always that clear. People are misusing these terms a little bit. So I want to at least try to clear this up a little bit here. So let's just give some hopefully proper definition of these terms with a few historical references. So let's start with artificial intelligence. What is that? I guess that's pretty much the one term that's likely the hardest, the most difficult to define. So this is a very general term for a very large and rapidly developing field and all of the associated applications of these fields, of this field. And the problem is there is really no super strict and super exact definition. It is often used to define solutions, to define algorithmic solutions where machines, probably should rather say algorithms, that usually refers more to software than to things necessarily in hardware, although there's of course robotics and so on, where let's say algorithms perform tasks that could potentially only be solved by humans before, but are usually quite difficult, and where we assume that some form of intelligence is somewhat helpful or required to solve these tasks. And you can already see me struggling here. Of course, there are, I would say, certain authoritative books on AI that have been written in the last decades. You could look at the outline of these books, and I would say that this gives a proper, good definition of the field, but it's like compiling different things people look at in this area, but it's very hard to give a mathematical super strict definition. So maybe it's a bit helpful if we look a little bit at history. So when did AI roughly came about? I guess you can have different perspectives on this, but one starting point could be in the 1940s. This was also exactly the point in time where the computer was invented. You might have heard of that. And there were people like Alan Turing, John von Neumann, who were very, very, important, were pretty much on the forefront of inventing the computer and inventing also mathematical models to describe what computation actually is. So the mathematical foundations behind what a computer and computation is. And interestingly, these guys were pretty much already interested in the question. So if we can formalize what computation is, maybe that's somewhat related to what intelligence is. Maybe we can already, using that formalism, we can now talk about artificial systems that simulate something that is intelligent. And maybe that's also, maybe these formalisms can also be used to describe what human intelligence is. What then happened is that the field somewhat branched out into many, many different sub-areas. So there's machine learning, and of course we talk a lot about this here. There's natural language processing, computer vision, robotics, planning, search, intelligent agents, and so on. And people historically have worked on all of these areas with different, let's say different speed of success. So there was this idea that things like vision, things like language, that this wouldn't be so hard to tackle in the area of artificial intelligence, but things like, planning, search, and then maybe using that to solve things like, chess or whatever, so automatic game playing, that this would really be the difficult tasks. So, and scientists usually like to work on the most difficult things first. Interestingly, in these areas, we saw some, I would say, rapid success, even in the beginning of artificial intelligence. Many search algorithms were invented in that field to solve tasks like automatic planning and automatic reasoning, and things maybe also associated with symbolic computing, the things which we traditionally call sub-symbolic computing, which we nowadays, I guess, call machine learning, and then which is also highly associated with things like computer vision and NLP and machine learning in general. These things turned out to be way harder. So constructing a search algorithm that could maybe, solve chess or maybe checkers as a simpler game. People were quite successful with that. But just figuring out or constructing an algorithm that can detect what is on an image, that turned out to be way harder. Nowadays, this term of artificial intelligence is sometimes also misused a little bit as a hype term. I don't like that too much. So when people want to refer to machine learning, and they sometimes just say AI, maybe they just want to refer to something like basic data analysis and so on. That doesn't necessarily help us in clean and clear and precise communication. Or people maybe refer to all of these interesting developments in current large language models or in computer vision and so on, which I guess is a little bit more in spirit of the original idea. Maybe one further thing that's you could even see as a paradox is, first of all, like I've said, there's not this super clear definition of what AI is. So it's a collection of interesting, challenging problems, and then, creating algorithmic solutions to these problems. What has happened historically in AI quite often is that a certain kind of paradox. So you look at a problem and you think, hey, this is very hard. Maybe we need some form of intelligence to solve it. Then we construct an algorithm to do that. And then you look at this and say, okay, this is like just searching over stuff. This is just like, computing some form of a function. So maybe this is not so intelligent at all. So in a certain sense, after we have solved some problems with, let's say, AI tools, AI methods, the solution doesn't seem to look that intelligent anymore. Whether this is still true for the things we are applying today, the jury is still out on that. But I want to move on now to talk more concretely about what machine learning actually is. So I would say machine learning is a little bit easier to define. So the reason is we have a little bit more precise mathematical language available to us. It usually tries to solve more narrowly defined tasks. Makes it a little bit easier to talk about it. But of course, the boundary to artificial intelligence is of course blurry. So usually machine learning, we say machine learning if we want to say that we are constructing some form of predictive model, some form of a function that takes some input, transforms it into an output, and that output is usually some form of a prediction, a label, some characterization of the input. And we don't explicitly program how this function could look like. Now you can approach this more from a statistical perspective, which I will mainly do for the rest of the lecture. So learning functions from data, learning their parameters, but you could of course also see this as some form of automated programming, right? So there's a computer program in the background, some algorithm, and that algorithm constructs another program that solves the task. That takes some inputs and outputs something. What we will here mainly talk about is constructing somewhat simple outputs, so classifying things, doing regression, so producing some form of a scalar output. And here's a historical, I think quite nice definition by Tom Mitchell, so a very well-known researcher in the area of machine learning, and that says a computer program is set to learn from experience E with respect to some task T and some performance measure P if its performance on T as measured by P improves with experience E. I guess it's a kind of a long sentence here, and we'll work our way through all of these different terms, like what is here, what is this performance measure, what is this task, what does learning mean, the rest of the lecture. Well, what I should maybe also say is that there are these different sub areas of machine learning. Already hinted at that. So there's like supervised machine learning here. Actually, let me switch on the pen tool. So there's supervised machine learning here, mainly pretty much exclusively focused on this here. There's classification, there's regression. We define exactly what that means. We'll study many different algorithms to solve these two areas, but there's also reinforcement learning and there's unsupervised learning. We'll not focus on that, or pretty much not talk about this at all here, but at least in this session, I want to briefly define what these two areas are in, 1 minute for each of them. And then you can start reading a 1,000-page book on both of them. Before we do this, now what is deep learning? That's fortunately also not so difficult to define. So deep learning is just quote unquote, just a very important subfield of machine learning. Just as we are studying a certain class of models here, and these models are neural networks. So what are neural networks, or maybe I should say artificial neural networks? So these are somewhat inspired by how the human brain works. So how neurons are connected in the human brain, how they do some form of, biological computing. But I really don't want to get into this here at all. I personally think that this analogy, it's fine to come up with these ideas. People have certainly been inspired by this, but I'm not an expert on, neurology, cognitive science. And I've looked into this a little bit. I would say as a layman, my impression is that our, artificial neural networks that we look at here are not super exactly close to what happens in the human brain. And I'm as a person, as a scientist, I'm not super interested in figuring out how close this connection is. Artificial neural networks are certainly a great tool in machine learning, and they are a mathematical concept that should also be studied as such, because we have to do this anyway. And I guess this is what I'm trying to do as a scientist. And the other stuff is more for people from cognitive science and neurology maybe. Okay, so is deep learning something completely new? Has that been created in the last, let's say, 20 years? Yes and no, so to speak. Neural networks have actually been studied for decades. So interestingly, this also studied started approximately in the 1940s. So there were two really seminal works by McCulloch and Pitts, and also by a person called Rosenblatt. They invented what the perceptron is, so what a single neuron is. They already were able to use that as a predictor. We were also able to talk about what these computational units could encode, and they were also able to start formalizing and start figuring out how to train these single neurons. And then, let's say, during the 60s, during the 70s, people were able to work with, reason about, do science on networks of these neural units. So we really had now neural networks in front of us. Of course, people were not so great with training them on larger data sets. The mathematics behind neural networks wasn't really that much evolved, or for machine learning in general. And we couldn't really train them on larger data with deeper architectures and so on. So in the last, let's say 20 years, we have become way better to use and train deeper networks with more layers, with super high dimensional parameter spaces, sometimes millions of parameters nowadays. We came up with specific neurons for image data, for natural language processing, and so on. And there were many, many computational improvements to train these beasts on large amounts of data. Neural networks can also be used on tabular data, but typical applications are usually some form of a tensor, so images, text, signals, and so on. Also, we have a dedicated lecture here in Munich on deep learning and neural networks. So I'll talk a little bit about, or we will talk a little bit about neural networks here, and we'll sometimes use them as examples, and there will be smaller sessions where we spend some time on studying neural networks, but we're going to do this here in depth because there is a dedicated lecture for this. And the last 15 to 20 years have really produced remarkable results when we applied deep learning to really, really challenging problems. And some of these results really looked like imitations of human ability, imitations of human intelligence. And this has been, I would say, really revolutionizing many, many fields with really, really interesting and exciting, sometimes also really scary results. And I'm sometimes reminded here also of this quote. It's a very old quote by science fiction author Arthur C. Clarke. It's sometimes called Clarke's third law. Any sufficiently advanced technology is indistinguishable from magic. Maybe, I don't know, you find this a little bit enlightening. Okay, so what does all of this have to do with statistics? Aren't machine learning and statistics completely different fields? Isn't machine learning pretty much, I don't know, a subfield of computer science? Again, yes and no. Again, explaining this is somewhat difficult, so let's at least try to do this a bit here. So, of course, historically, I'm not sure whether I should say of course, but historically, statistics and machine learning have evolved as different fields with different persons and different communities. You could even say that progress in machine learning and underlying theory has been studied and developed in different fields. But let's not complicate things any further here. Let's pretty much focus on the relationship between machine learning and statistics. So I would say, although they have developed in different fields, in different communities, if you look at the maths, and I'm hoping that this lecture here helps you to do that and teaches you how to do this, you will figure out that many methods and many concepts are pretty much exactly the same. If you want to try out a distinction, you could say that machine learning rather historically focused a bit more on producing more complex models and with the goal in mind to construct really accurate predictors. And statistics focused a bit more on constructing models where later on the goal was rather understanding the relationships between inputs and outputs in a stochastic, in a statistical sense, doing things like inference and so on. But first of all, this black and white view is even historically inaccurate and not true. So in statistics, people have looked at non-parametric models and non-parametric techniques for decades. And that's pretty close to what people in ML have been doing. And in machine learning, yeah, people who are also interested in explaining how models work. XAI, interpretable machine learning, has become extremely popular in the last 20 years, but people have been looking at questions like that before in the field. And the other thing is, if you look at the mathematical language that machine learning is written in, that is pretty much probability theory and statistics. So nowadays, I would say both of these fields basically work on nearly the same problems with the same tools. Communities are unfortunately still divided. Sometimes terminology is sometimes extremely confusing because there's like 5 different words for the same concept. And it's very hard to understand that if you haven't studied all of these fields for years. If you want to have like a 1-sentence definition of machine learning, from me, you could say it's something like non-parametric statistics plus efficient numerical optimization. Of course, these 1-sentence definitions always fall short a little bit, but I guess this is approximately correct. And yeah, here's another personal opinion. Nowadays, I would really say there are very few practical differences. Seeing differences instead of commonalities between the fields, I would say, holds you back more than it enlightens you. Right? There are a lot of texts out there, papers and blog posts which talk about the differences. I think it's quite helpful actually to figure out the commonalities. And I would encourage you, if you're, I don't know, to come back to that question after you've looked at this lecture for some time, after you've studied both of the fields, read things from stats, read things from machine learning, educate yourself on all of these different areas, and then maybe come back to that question. And I guess maybe you agree with me, maybe you don't. Okay, let's wrap things up by, I promised I wanted to at least define in 1 or 2 slides what unsupervised learning and reinforcement learning is. So what is unsupervised learning? So in unsupervised learning, we have usually data without labels. What labels exactly are, talk about later. So it's outputs, right? And we want to, in supervised learning, we want to learn the relationship between inputs and outputs. In unsupervised learning, we do not have these observed outputs, but we are still searching for patterns within our input data, right? So maybe we want to look for, I don't know, clusters. We want to describe how these clusters are located in input space, how they're distributed. Associated techniques might be something like PCA, principal component analyses, more modern autoencoders. So we might talk about compressing information in X, or I guess you can see this visually here, clustering, grouping similar observations, and then later on studying what these clusters actually might mean. Outlier detection, so is an observation, potentially a new observation out of distribution. Anomaly detection, constructing association rules, so rules that encode how certain features relate to other features. But there's not like one specified dedicated output that we want to map our inputs to. What's reinforcement learning? That's, I guess, an even more general field. You could see this as a general purpose framework, maybe even for things like AI. It's also super helpful to talk about, to use that and to talk about agents, to talk about robotics and so on. So the idea is here that we have something like an agent, visualized by this brain, and this agent interacts with some environment. Could be the real world, could be something that's, I don't know, artificial or simulated, and it observes some state of that environment. It executes actions, and based on these actions, it then receives a reward depending on what goal we want to make that agent learn, so to speak. And the usual idea to mathematically formalize this is to learn a policy so that over time we select actions to maximize future reward. Problem is that these reward singles, they might be sparse, they might be noisy, they might be delayed, and have to somehow figure out how from these sparse, noisy, and delayed reward signals we can learn efficient policies so our agent interacts in this environment with maximal reward over time. What will happen next now in this lecture? Actually, digital material spans multiple lectures here in Munich. So we'll now begin to more and more formalize what we mean by supervised learning. We'll specify what we mean by regression, specify what we mean by classification. So we will study how to automatically predict labels based on feature vectors, based on training data, and automatically construct functions which do this. And we'll start out here by going now through fundamental concepts in supervised machine learning. So we'll define what we actually mean by data. Where does this data come from? Yeah? What is a prediction model? How can we actually quantify how well a prediction model works? What do we mean by predictive performance? What is actually a learning algorithm? How can we mathematically formalize that? How can we operationalize that? And of course, we will then study a different array of simpler and then later a bit more complex learning algorithms. So here we'll focus first on linear models, mainly because they're simple to describe. They're a good starting point, still very useful for some tasks. And then we'll look at trees and we'll look at our first ensemble technique, random forest, which is already a pretty powerful and still very popular and very useful machine learning model. Later on, we'll talk more about neural networks, Gaussian processes, support vector machines, parameter tuning, and so on. But all of this comes later. Now, okay, I hope you enjoyed this here. See you in the next session.